Hi, everybody. I'm Jeff Clayton. I'm the Interim Director of Astronomy here at the Environmental Association. And today we have a very exciting event. As most of you know, every summer we have several students come here to participate in research here at the Environmental Association. It's part of the Research Experiences for Undergraduates program from NSF. Today we've got 5 students here who are going to give their talks on the projects that they've been working on all summer. And we're going to start with Kaylee Perez, who will tell you about herself.
Hey, hooray. Hey, hello, everybody. Thank you all for coming. As mentioned, my name is Kaylee Perez. I'm from Texas State University. I'm an uprising senior. And my project this summer was on how dust changes the light we see, exploring the link between dust extinction and attenuation using simulated data. Now, naturally, the question arises of what is extinction, what is attenuation? But for that, we need to know what dust is. So what is dust? And no, I'm not talking about the dust underneath your couch, and which is a good guess, but not what we're talking about today. What I'm actually talking about is cosmic dust, the tiny solid particles that are floating around in between stars and galaxies. And so these grains are very tiny, about 1/10 of a micron across, which is about 1,000 times smaller than a human hair. And so this type of dust comes in 2 types. There's silicates and carbon-based grains. And these grains all come in different shapes and sizes and all interact with light differently. And so that's where it gets interesting, because depending on what kind of dust you have and what color of light that you're looking at, the effects can be very different. And so the next piece is how dust actually changes what we see. So going back to the dust in your house, most of the time you don't notice it until sunlight goes into your home. And suddenly you see all these tiny dust particles floating around. What changed? The light interacted with the dust. So this dust was redirecting light and dimming the light. And so that's what makes it show up in that sunbeam. But cosmic dust works the same way. On the scale of the universe. Okay, so on the scale of the universe, we describe this in 2 ways: dust extinction and attenuation. So,
one moment of a pause. Zoom difficulty.
okay, anyway, back to it. So if we're looking at a single light source like star, and there's a cloud of dust in front of it, the dust will absorb some of that light and then scatter the rest. That dimming and reddening of that light is what we call extinction. So absorption plus scatter. But usually when we're looking at things in the sky, we're not just looking at one single star, but multiple stars. And there's a bunch of dust between it, in front of it, and behind of the stars, and they all interact with the dust itself. And when we get that, we get extinction plus the geometry of where the dust is. And so attenuation is messier, and the mass is exactly what makes studying galaxies very, very tricky. And so this really matters because dust doesn't affect all light equally. It has the strongest impact in the ultraviolet, and right where young stars shine the brightest. Now, this isn't something we see in one small cloud. the effect shows up in entire galaxies. So each galaxy has its own distinct properties. And here's a spectral energy distribution of different types of galaxies, which just shows how much light we get from galaxies at different colors of light. So here on the x-axis, and get the laser out. On the x-axis, we have the color of light or wavelength. And on the y-axis is the amount of light at each color wavelength. So now astronomers often use a standard model of attenuation to correct for this, but that model was only for one type of galaxy. And we apply it to all types of galaxies, we get incorrect results, underestimating, overestimating different key properties of galaxies. And so that's why it matters to study attenuation more carefully. And that's where my project comes in. So here's the question I set out to answer. How much does dust change attenuation? So how did I test this? Let me walk you through the data and the fitting process. So for this project, I didn't use telescope data directly. The data I'm using is simulated. It's generated by something we call radiative transfer modeling. And this just means it simulates how light interacts with the dust as it travels. Some of the light is absorbed, some of it is scattered in other directions, and some of the light comes through to us. By using radiative transfer modelings, the simulations gives us both extinction curves, so what the dust itself does, and the attenuation curves, what is happening in between the stars with all of the dust mixed in. And when we run those simulations, we can run them with different types of dust. And so here are the three models I'm working with. They're based on the environments of the Milky Way, large Magellanic Cloud, small Magellanic Cloud, and despite the names of clouds, these are actually whole galaxies, just smaller companions of the Milky Way. They're close enough that we can study the dust in detail, and what we find in each galaxy is that each one has different kinds of dust. To see this difference more clearly, we can look at their extinction curves. So this is the baseline signature of how dust absorbs and scatters light in each galaxy. So here on the x-axis is the wavelength or the color of light, and on the y-axis is how strongly the dust affects the light. So one thing to notice is that on the Milky Way, we have this big bump, and that bump is speculated to be caused by carbon-based grains like pals and graphite, which absorb light really strongly at that wavelength. But when we look at the small Magellanic Cloud, that bump disappears. And that's speculated because the SMC has harsher environments, and we still don't know what that answer is. But if the difference is one of the reasons extinction and by extension attenuation is just much more. We can't use it for one single law. If we use one model for each one, we just don't get the same results because each of them have different properties. And so this model is only half of the story. The other half is geometry. In these simulations, geometry comes in two flavors, global and local. Global geometries describe large-scale structure of the galaxy, whether it's surrounded by a dust shell, or if it's combined in a dustier environment, or just cloud events. And the other geometry is local, so whether it's embedded evenly around in a homogeneous way, or if it's clumpy and tucked into clumps in between the stars. And so this shaded region, the lighter shaded region is the homogeneous, and the clumpiness is those darker squares. And so here's the setup. We simulated galaxies with three types of dust grains, Milky Way, OMC, SMC, each modeled with three global geometries, cloudy, dusty, shell. And those are all with homogeneous or clumpy forms. And so on top of that, we varied the optical depth, so the amount of dust that we're looking at. And altogether, this gave us 145 different combinations. So that's a lot of geometries. So to probe the role of geometry in attenuation, we need to find a way to separate that dust physics, the absorption and scattering, from the geometry. That's where the FM90 model comes in. The FM90 model is a dust extinction model. On the x-axis, we have wavelength, and on the y-axis, we have how that dust affects that light. And so this black curve is the full extinction fit. But FM90 actually builds this curve from three pieces. So this blue line indicates the overall slope or the baseline trend. And the orange bump is the ultraviolet feature at 2175 angstroms. And the green curve is that far UV rise that are caused by very small gradients. And so by adjusting these parameters, FM90 can match very, very different extinction curves. So now our technique was simple. We take FM90, which shows us how scattering and absorption is working, and fit it to attenuation curves from our simulations. If the fits work well, the geometry didn't do much in this absorption and scattering, but if it breaks down, geometry is leaving a fingerprint. And so now let's take a look at what that looks like with our data. Here's an example of what that looks like with the Milky Way, or a cloudy, clumpy geometry with low dust amounts. This black line is the attenuation curve from our simulations, and the teal line, dashed line, is the FM90 model fit. This colored dots are the components that make up this curve, and right under here is the extinction fit and the simulation underlying extinction curve, just for a baseline of the scattering and absorption. So you can see that the FM90 model is capturing the main features of the bump and the UV slope, but it's not perfect. Those little mismatches between the data and the fit are where geometry is sneaking in and reshaping the curve. So since FM90 was originally built for the Milky Way dust, we expected it to perform the best there. And in many cases it did. It fit everything to its best ability, and it did it quite good within the error terms. But I'm only showing, so now that we tested the fitting, we can now see how attenuation curves vary with optical depths and different types of geometry. So that's this part. So here's the same geometry from the previous slide, and now with varying dust amounts. Notice the trend. So with very little dust, we can see the bump very clearly, the slope is very defined, but when we add more dust, the curve flattens out. And the FM90 still does well. It's shown here in the dashed lines. And this tells us the model is still capturing the main dust physics, even across different dust amounts. But now, if we change the geometry to other ones entirely different, we get the same trend. So here we have the amount of dust, so optical depth, and here we have the UV bump strength that's from one of the parameters of the FM90 model called V3, and each color defines a different geometry. And so we can see the trend going down of the bump going down as more dust is being introduced. And the FM90 model, again, is fitting these all quite well when we run through all these simulations. So this tells us that optical depth is a dominant factor at shaping these attenuation curves. But let's remind ourselves what a good fit looks like. Here is a Milky Way again for a cloudy, clumpy geometry with low dust amounts. And you can see that it's fitting it very well. The bump is there, everything's within the arrows. But when we move to the LMC and SMC, that's where the picture gets a bit messier. The fits are not nearly as good, as you can see. The LMC here is not getting all of the shape of the curve. It can't, the fitting of the FM90 model is trying to get the bump and the slope simultaneously, but it just can't, it's breaking down. And then when we go to the SMC, it just doesn't fit it at all. So that's because our simulation data is trying to fit a concave down slope, but the FM90 model was built for a concave up slope. So those just don't add up at all. So while the FM90 worked fairly well in the Milky Way, the LMC and SMC fits break down. But this progression shows us that geometry alone doesn't explain attenuation. The intrinsic properties of the dust play a huge role. And so moving forward, this will be the next steps. I'll extend the analysis across all geometries of the LMC and SMC dust models, compare the fitted parameters across different geometries, and quantify how good they really are. And beyond the simulations, we'll be comparing to the results of empirical data, so real observations. And then by doing that same exercise that you saw previously to observe dusty galaxies like this one shown, we can test how well our simulated insights hold up in the real universe and identify where we need better dust corrections and overall better dust models. And in short, the goal is to untangle how much of attenuation is pure dust physics and how much is geometry, and then check how well those conclusions hold up in the real universe. And so that concludes my presentation, and thank you all.
We're going to hold all questions until the very end, so hang on to your questions. We're going to move on to our second talk now by students who are sharing the same project, Ben and Aiden, and take it away.
You can call it, you can't see it now. Okay.
Apologies.
One more trick. What's the point there?
I think you need to have it connected while it first present it while it's connected and then share it to the Zoom.
Keep it connected all the time.
Connector. Okay.
Split between your screens. It might just be on your other desktop. Because we can see it online.
Okay. Can't even see my cursor.
Click on
Click on PowerPoint.
This.
it. So now
And then.
Now share.
I don't see that on this though.
That's because you're not in sharing it in Zoom.
Okay. So Zoom. Share. Let's go to share.
Okay.
Okay, sorry. Skip there.
Take it away.
Cool. Hi, everybody. I'm Ben. I'm a senior at the University of Michigan.
And I'm Aiden, and I'm a junior at the University of Montana.
We've been working directly with Jeff Clayton as our advisor, along with some support from a Space Telescope Science Institute team that's led by Ori Fox. The team focuses on a bunch of different supernovae, but we will be focusing on supernova 2011 JA in particular.
So before we get into our specific project, we need to talk a little bit about what a supernova is in general.
Nope. Zoom smudge.
How many physics students does it take to get?
Is it good on Zoom?
I mean, the first slide is there.
Well, let's start.
So you just switch the slide in PowerPoint. You don't do anything in Zoom.
I don't have it in PowerPoint. I don't know how you're seeing it.
There
Oh,
you go.
Ah, okay. Okay, we're good. No, let's start with what a supernova explosion is. So a supernova is an explosion that occurs at the end of a life cycle of a very massive star. So in this scientific context, massive refers to how much stuff something is made of, not how big it is. So you can think of it a little bit like weight. Only stars that are at least 8 times as massive as our sun will supernova. And before stars will explode at the end of their life cycle, they're constantly pushed in by gravity. So there needs to be something that holds them up for the duration of their life. So while gravity is pushing in, stars are fusing. When they have nuclear fusion in their core, they're kind of smashing elements together, starting at hydrogen. Those hydrogen atoms will turn into helium and so on and so forth down the line. You can get elements like carbon, oxygen, and all the way down until you get to iron. But iron is the point where the star can't fuse anymore. And that's because Mother Nature doesn't like to sweat, and a reaction past iron takes more energy than it puts out. So we only like to do reactions of nuclear fusions that are going to provide energy for the star. So once you hit iron and you stop fusing, you no longer have that pressure from inside the star to hold it up. So gravity can scrunch it down and it collapses really rapidly until it hits a certain point where its particles can't get any closer together. And that's called neutron degeneracy. And at that point, the sudden stop sends off a huge shock wave, which kind of rips off the outer layers of the star. So you get these shells of hydrogen, helium, carbon, oxygen, all of the elements that were making up the outer parts of the star being blasted off out into space. And then what's left over in the core can collapse down and become either a neutron star or a black hole. There we go. So then after the supernova explosion, you have what's called a supernova remnant. The remnant is the external part of the supernova. And then what's left at the very middle is the neutron star or black hole that we talked about earlier. So the remnant is made of 2 components, the supernova ejecta and then the interstellar medium, which is all the stuff that exists around the star. And in the modern day, we've never seen a supernova here in our Milky Way, but we've seen them in other galaxies, and we've seen remnants of supernovas that exploded in our galaxies a long time ago that were well studied and documented by famous astronomers such as Tycho Brahe or Johannes Kepler. And so we can study these remnants. They're made of mostly gas, and somewhere kind of around the shock wave that ripples out from the supernova explosion, you also get this dust that starts to form in addition to the gas that's left over.
is it changed on the Zoom? No.
Thanks for bearing with us.
I'm gonna stop sharing and unplug again.
Don't unplug, just
Well,
stop.
the slide is definitely part. Shouldn't. That's what I used for Python.
I suppose that we actually were coding this thing.
Okay. Is it
Yeah.
normal? Fantastic. Right here. Yes, okay. Kaylee has given us a brief introduction to dust, but for our intents and purposes, dust is just two things. It is carbon and silicates. So carbon-rich dust is a lot like soot. It's the kind of stuff that you find in the back of your barbecue. Silicate-rich dust is a lot like sand. You get it stuck in your sandals, that kind of thing. We can tell these types of dust apart by their spectra. So different chemicals, when heated, emit different colors of light. We can look at many different size wavelengths of light, not just wavelengths we can see and know to be the colors. The colors closest to visible light on the blue end of the spectrum are ultraviolet, and on the red end of the spectrum are infrared. The shape of dust's entire light curve in every wavelength indicates exactly what the dust is made of. These graphs have wavelength here on the x-axis and then flux density on the y-axis. You can think of flux density as the amount of light that the dust is putting out at a certain wavelength. We don't have to look in every color to know what chemical we're looking at. We can focus on specific wavelengths with specific telescopes. When we look here in the mid-infrared range, we notice that there is a really large bump here, which we call it a feature. In our silicate spectrum, but this bump is entirely absent in the carbon emission spectrum. In reality, dust will always sort of contain a little bit of both. So we can also try different temperature and mass combinations of carbonates and silicates to see if we can figure out a combination of the two components that would best match our data. Once we get models like this for any given supernova, the model will also give us an indication of how much dust the supernova has created.
But why do we even care about how much dust the supernova creates in the first place? Well, galaxies at high redshift have lots of dust. And this is a little bit strange. So in this case, a galaxy being at a high redshift means that it's very old. And these old galaxies are really, really dusty. But dust doesn't just appear out of nowhere. There are lots of different ways that dust can be generated. Our Coronae Borealis stars, which Lauren is going to tell us about, are one way that dust can be created. Some Wolf-Rayet stars can create dust. And then there's also the dust generation around supernova shocks that we've already talked a little bit about. But when the universe was that young, these other kinds of stars besides supernova couldn't have been around to produce this kind of dust. So we suspect that supernova are the big producer of dust in this galaxy. But we don't really know how much dust the supernovas create on average or how that dust evolves over time. So the natural question is, how much dust can a supernova really produce over its lifetime? And there are lots of astronomers trying to answer this question. This is kind of the big plot. This graph represents all of the supernovae that have been analyzed for dust production up to this point in time. So on the x-axis here, we have epoch, or that's a fancy astronomer word for just time, in days post-explosion. And then on the y-axis, we have dust mass. So that's how much dust there is around the supernova. And the same supernova might be on this graph at a few different places if we've measured dust masses for it at several different times since it has exploded. And we can see that there's kind of a gap here at mid, late, and then extremely late times where we don't have as many data points as we do at really early times. So we would really like to have kind of more data to fill in this group so we can get a better sense if supernova really can be the big dust producers in these early galaxies. Our supernova falls within this time range, so it will produce a data point for us to add to this overall graph.
A little bit about our supernova. So this summer, we've taken a special interest in supernova 2011 JA. This is a supernova that exploded in the galaxy NGC 4945 14 years ago. 2011 JA is a type 2 supernova. That means that we detect hydrogen in its emission lines. Specifically, 2011 JA sits at the border between a type 2L and a 2P. So 2L means that the supernova has a linear decrease, L linear, in light over time. 2P means that the supernova plateaus, plateau P, at one brightness for a little bit before starting to decrease. 2011 JA plateaued very briefly before linearly decreasing in brightness. Work has been done on 2011 JA in the past, notably by Jen Andrews, Maddie's summer REU mentor. She identified about 1/10,000th of a solar mass of dust being generated around the supernova, and about 1/1000th, of a solar mass of dust already existing in the space around it. The mass of progenitor star of 2011 JA, so the original star before the supernova, was also estimated by Dr. Andrews, and it's estimated to be potentially larger than 25 solar masses, so 25 suns. 2011 JA was identified as interesting by our current program due to some recent Hubble images that were taken of it, which seem to show a light echo around 2011 JA's location. A light echo occurs when light from the supernova is reflected towards Earth off of material near the supernova. It's similar to sound bouncing at you with a sound echo. Through Ori Fox's JWST, so the James Webb Space Telescope, dust program, we've accessed some new images of 2011 JA, which we used to explore dust formation very late in 2011 JA's lifetime.
So like Ben said, our project used James Webb infrared images. So we have an artist's rendition of James Webb over here on the left. It's a space-based infrared telescope, and infrared telescopes have to be space-based because of this little gap right here. So this is showing that the Earth's atmosphere doesn't let infrared light down to the surface. So we have to use telescopes that are up in space. We have 8 images taken with MIRI specifically, and MIRI stands for the mid-infrared instrument, and that's on James Webb. So we're looking at mid-infrared light because dust in space is very cold, and cold things glow in infrared. But there's actually another space-based infrared telescope that has previously imaged 2011 JA, and that is Spitzer. So Spitzer is on the left here. It was launched in 2003, and it imaged all the way up until 2020. And this is a comparison of the resolution between Spitzer on the left and then Webb on the right. And we can see that Webb gives us a lot more clarity on what's happening in these really dense regions here. So we see much clearer these kind of tendrils of dust. But the benefit to continuing to use Spitzer data today is that it caught the location of the supernova in an image right before it exploded and then right after it exploded. So we get a really clear view of this burst of light coming into existence. And you can see those images shown here. So the red circle is where the supernova's location is in all of the images. The top row is the 4 Spitzer images taken at different times. And then the bottom photos are all from Webb, and these are taken at the same time, but in different wavelengths. So the top left shows the location of the supernova pre-explosion right here. And then the very next image, we see this really bright blob up here, and that is the supernova after it's exploded. It's very bright in that Spitzer image, but you can see that the supernova is a lot fainter in these James Webb images. They were taken much later in 2023. And so if you were looking at the James Webb images with no guide, it's not really immediately clear which dot is the supernova, especially because the resolution is so much better than the Spitzer resolution. We can see a lot more specific dots, so we have more options. So we needed a process to make sure that we were looking at the same dot between the James Webb and the Spitzer images.
So as a little bit of a zoom in, the reference image here on the left is the supernova in that very bright Spitzer image that we were just looking at. The bright spot here you see in the middle frame is the supernova in our pre-alignment Webb data. So Spitzer and Webb are 2 different telescopes. Objects might end up at slightly different places in the final images because of uncertainty in where the telescope is pointing. Even just a little imperceptible change in angle can totally throw off where we believe the supernova to be. The alignment code, the process is called alignment. Our alignment code picks out several bright stars in the Spitzer images and lines them up to match the same bright stars in the Webb image. It was very essential that we pick a Spitzer image that has a whole lot of stars, as well as a Webb image with the exact same visible stars. So we use the Webb image in the wavelength closest to Spitzer, so that's at 5.6 microns. The alignment image here is also kind of misleading. The pixel size in Spitzer is much, much larger than Webb, as we kind of saw in that in 2 slides ago, I believe. So this leftmost image we are looking at is a much larger region than these 2 regions on the right. So the realigned Webb image is on the right here. It's just a little shift. And it is centered now on the same coordinate that it is in Spitzer. We then use a process called bootstrapping to match the coordinate system in all of our other Webb images, so at longer wavelengths, to our newly aligned lowest or highest wavelength Webb image. We are allowed to do this because the images were taken with the same instrument all together on the same telescope. So it's a much simpler process. Then we perform photometry. When we perform photometry, we measure the flux from an object, which is, as we said before, the amount of light being emitted. There are many sources of light in this image. You can kind of see them, especially in the 5.6 micron images here. There are a lot of sources of light in the image, including background contamination from other really faint sources in the galaxy, or even background galaxies. So we also know a very bright source in the upper right of each of our images, which really dangerously interacts with the supernova's light, especially at that longest wavelength here. So we create a model based on the way that the telescope, in this case Webb, takes in light, and we subtract that model from the location of the supernova, and the light that we subtract is the total flux of the supernova in that particular wavelength. So what we're looking at, here we have examples in 3 filters that show the original data, the original telescope data, in this leftmost column. The sort of background ambient light in this column, the model we construct of the supernova, the model and the background added together, and then the residual. The residual is the data with the model and background subtracted away from it. If that residual looks smooth, so if there isn't really a super big standout hole in the data, we know that we did a good job at building our model of the supernova. It's also worth noting that the supernova sort of becomes fuzzier as we go down into the longer wavelengths. And the further into the infrared we go, the more our point sources kind of spread out, and we have to contend with interference from other sources in the background. But using this method, we found flux values for all 8 of our filters. Those flux values are plotted here in black with some estimated error bars. It's important to note with this graph in particular, that finding the error on our photometric process is really, really hard. That is actually the main goal of one of our collaborators at the Space Telescope Science Institute. So that is a constantly evolving process. But again, we have wavelength on the x-axis here and flux on the y-axis. We use a statistical process called Markov chain Monte Carlo to fit a range of different parameters to our data points. So this MCMC process runs through a whole bunch of parameter combinations. In this case, the parameters we're looking at are the mass and the temperature of our dust, and it runs through these in order to find a combination of parameters whose light curve best fits the data we give it. We also provide the MCMC with what we call priors. So these are bounds on parameters the MCMC is experimenting with, so that it focuses only on kind of realistic parameters when it's exploring that parameter space and helping us to construct our model. The green line that you see here is the dust model that we were able to fit to this data. It's a 2-part model. The red and blue dotted lines are 2 components of carbon dust at different temperatures and masses, which combine to add up to give us this closest fit to the observed data in the green line. Earlier, we showed, as you may remember, that carbon-based models don't have that bump and silicon-based models do. We don't really see that bump in our actual data here, so we only fit using 2 different carbon components. The model fitted a hot carbon component, that is this red piece, at 258 degrees Kelvin, about 5 degrees Fahrenheit. So not hot to us, but you know, it's all right. And a colder carbon component at 107 degrees Kelvin, which is about negative 270 degrees Fahrenheit. Very cold. The mass of hot dust is very, very low. It's about 1/1000th of a solar mass, but the mass of the cold dust is really remarkably high. It provides the majority of, there's about half a solar mass of dust that we discovered in total around this supernova.
So now we have a mass of dust around our supernova at a specific given time. So as a reminder, this is what the big dust plot looks like before we added our data point. And I want to point out, we have a few points that are actually from earlier observations of 2011 JA. So these are dust masses that were calculated earlier in the evolution of its life cycle. And now we are ready to add our dots to the graph at over 4,200 days post-explosion, right around about 0.5 solar masses of dust. And so as we continue to tweak our modeling, this value may change slightly, but out of all of the different models we've tried with many different compositions, many different priors, we've never gotten a value below 0.1 solar masses or above 1 solar mass. So that's what the black bars are showing right now. Based on our current value, this means we have around half the sun's weight in dust hanging out around the supernova. So let's take a look at our point in context with all the other points.
Yeah. So looking at our supernova here in context, we can note that it's a very sparsely populated region of the graph compared to these earlier epochs with a really dense population of supernova, you know, a few hundred days after explosion. On the scale of this, on thousands of days, we note some similar dust masses, especially up here, but we can imagine a number of different trajectories given the lower population in terms of when that dust was generated. So while a high dust mass at late time, like we see here, is definitely not inconceivable, we can see that, as we can see sort of here, right, in some of the points nearest the supernova, this placement favors dust generation or an interpretation of dust generation that happens at a mid to late epoch in the supernova's life, which is important to note. Error bounds, these black bars, are going to be absolutely essential when we're making a claim like that.
All right, so moving forward past this point, as we look to the future, there are a few more things we would like to continue to include in our work. And the first one is we'd like to use the Moccasin program to run a radiative transfer model, like what Kaylee was talking about, and get like a dust mass and a heating mechanism that we can compare to our current value to make sure they're kind of in the same realm and agree with each other. And there have also been more Spitzer images taken since Dr. Jenna Andrews did her analysis in 2016. We'd really like to run some photometry and analysis on these images to kind of fill in the gap between 2016 and today and make sure we have a picture of 11J's evolution through that whole period of time.
There are also some goals we have for the far future, whether that is us pursuing them or others. We are interested in investigating the Hubble echo that we previously mentioned. It is not visible in our web data, but we welcome any input on how to explore and identify it. We would also be interested in viewing 2011 JA at very late time epochs, so decades down the line, to see whether the dust mass now remains constant. And then we would also like to encourage the astronomical community at large to generally examine supernovae at these late time epochs to further populate that late time region. But I promise you, astronomers need no encouragement. Thank you so much.
Thank you.
Okay. Our next talk is by Gerard.
normal on Zoom. Yeah.
And good go.
Okay. Is it still going? Yeah, okay, perfect. So hi, everyone. My name is Maddie Gerard, and I am currently a rising junior at the University of Texas at Austin. And this past summer, I have been working with Dr. Jennifer Andrews at the Gemini Observatory to observe the low-luminosity Type 2P supernova 2024 ABFL. And so before we kind of get into the analysis, I'm going to highlight some of the essential concepts, most importantly being what is a supernova. Now, Aiden and Ben kind of went over this, but we're going to do it again for the sake of my presentation as well. Will not do it. So there we go. So to understand what a supernova is, we need to talk about the life cycle of a star, which is mostly determined by its mass or how much material it contains. Mass can determine a lot of really important qualities of a star, such as its size, temperature, brightness, internal structure, and crucially, how the star ends its life. Today, we're going to be focused on the path of more massive stars, as we can kind of see. My cursor is very sensitive. And as they evolve into red giants and eventually supernova. But we're going to ask, how does this happen? So stars exist in this balance that we call hydrostatic equilibrium. And this balance exists between two opposing forces. So we've got an outward force from pressure or from fusion, and that is occurring as the atoms kind of smash against each other inside of the star's core. And then we've got an inward force from the star's own gravity, which is caused by its mass. And as the star ages, it's going to gradually fuse through the elements, hydrogen, helium, and then heavier elements such as carbon and the neon, as we can see over here. And the cores will get denser and denser, and fusion will start to slow down. And eventually, these fusion reactions will reach iron. But kind of as Aiden said earlier, Mother Nature don't like to sweat, and iron is not energetically favorable, so it just won't fuse. And so without this pressure from fusion, the star will just kind of collapse under its own weight. And this is what we call core collapse. And so this collapse will lead to a rebound shock wave that will explode the star in a supernova, which will briefly outshine all the other stars in the galaxy. And so here I'm about to play a simulation of the supernova 1987A, which is one of the most famous core collapse supernova ever observed. And it's a great example of the process that we just talked about. So you can see the progenitor star in the middle, that initial explosion flash, and then kind of how the blast wave is expanding outwards and it starts to interact with the gas rings that are surrounding the star. And it was actually the nearest supernova in over 400 years, so it was really great for analysis for astronomers. Moving on. So we have two main types of supernova, very creatively named, type 1 and type 2. And we're going to be focusing on type 2 supernova, which are core collapse supernova. And again, here you can see 1987A before and after. It kind of goes supernova. And one of the key features of these type 2 supernova is that they have hydrogen in their outer layers. So when we're observing them, we are seeing these really distinct hydrogen lines in their spectra. And type 2 supernova can even be further divided based on the shape of their light curves, which is how their brightness will change over time. So we've got type 2P, or plateau supernova, where their brightness is going to stay roughly constant before kind of rapidly dropping off. And then you'll have type 2L, or linear supernova, which show more of a gradual decline after reaching their peak. We can also have low luminosity type 2 supernova. And these are really dim events, and they only make about 5% of these type 2 supernova. And when they're compared to their more luminous counterparts, they're going to have slower expansion velocities, smaller explosion energies, and lower nickel masses. Now we're going to talk about my supernova 2024 ABFL, which was discovered on November 15th of last year. So it is very recent and very new. And based on pre-discovery imaging, we actually discovered that it can estimate that it exploded about 2 days earlier. And we are lucky that this part of the sky had been imaged with kind of a high cadence, meaning that we had a lot of images taken right before and right after the supernova appeared, which really allowed us to kind of pinpoint the explosion time with a high accuracy. So here I've got a GIF, and it never starts from the beginning, but if you focus on this spot right here, you can see right now there's nothing, and then all of a sudden we've kind of got this black dot filling the center, and that will be our supernova. So what we do to estimate our explosion time is we take the last date where we're seeing nothing and the first date where we're kind of seeing that explosion, and that's when we're going to estimate our explosion time to be. Going back to this very pretty picture, ABFL is located in the galaxy at the very edge. It's this kind of white dot that's marked by those lines, and it's located in NGC 2146, which is about 15.6 megaparsecs away, or 50 million light years away from us. So when we say, like, we saw its light in November, but it's actually exploded much, much longer ago than that, and that's just when we're getting the light from it. And then we are classifying it based like on our observations as a low luminosity type 2p supernova. And I'm going to walk you through how we got to that conclusion based on our light curves and spectra. So before we interpret these observations, we have to correct for something really important, which is dust extinction. As you can see, dust is kind of our overall center of the topics today. So dust between us and the supernova can scatter and absorb much more blue light than it does red light. And as a result, our supernova is going to appear redder and dimmer than it actually is. And so to correct for this, we can use two methods: sodium absorption lines, as seen here, which are really good indicators of how much gas is present. And we can kind of plug this amount into an equation and figure out how much dust is there. And then we also have galactic dust maps, which tells us how much dust lies in our own Milky Way along our line of sight. So by combining these both, we can calculate a color excess of about 0.2 magnitudes. And while this number isn't huge, it does matter, especially when we're comparing our supernova to other supernova and calculating intrinsic properties such as temperature and luminosity. So we are applying this amount to all of our observations we're doing in the future. And speaking of observations, to study 2024 ABFL, we gathered observations from multiple telescopes located at observatories kind of around the country and even in space. So these ground-based and space instruments allowed us to collect a broad range of both photometric and spectroscopic data across different wavelengths. We observed in the UV, optical, and near-infrared, so a wide range of wavelengths, and each of these regions are going to tell us something different about the supernova. However, they do also come with challenges. So as we can see from this graphic, our UV light is pretty much all blocked when it's coming through Earth's atmosphere, which is why, going back to the slide before, our Swift observatory is in space, and that's what's collecting our UV data for us. Then we have our visible range, which is marked by the rainbow here, and it's the part of the light that our eyes can see, and that's where most of our telescopes are going to be collecting light from. And things like altitude and weather are going to be distorting our data a little bit, but it is the best range to collect light in for the observations that we're going to be doing. And then we are observing in the near infrared, which is a little bit redder than visible, but not as severe as the mid infrared, which were where Aiden and Ben's observations were taken in. So we actually can get these observations from Earth, and we don't have to be up in space to get them. And so by combining observations from across the spectrum, we can build a very clear picture of supernova's behavior. And to kind of jump into that, here we have our first kind of data of ABFL, and this is a light curve, which is a plot of magnitude on the y-axis versus our time versus from the explosion. And so in astronomy, magnitudes are a way of measuring stellar light brightness. So we can kind of see it decline over time from its explosion. And when we zoom in on these first 10 days and this kind of plot off to the right, we can see, especially in this R band, which is the orange dots, we had our first observation of the R band, and we can see it kind of rise to brightness for the first time when the supernova originally exploded. And I mentioned bands. So when we're observing with our telescopes, we're going to use filters to isolate specific wavelengths. So each color on this plot actually represents a different filter. And these can help us track how brightness evolves across the spectrum. So our different shapes as well also show different telescopes. We've got circles, triangles, squares, and they're all telling us what different instruments were used. So over on this side, we've got our UV observations. So these are the ones that were taken up in space, and they let us track some hot early emissions that were going on. Most importantly, though, in the green, we have our V band, which is the visual band. So this band lies in a region from the Earth's atmosphere where it's highly transparent and the detectors are very sensitive. Because of this, it is the most widely used filter for tracking supernova brightness. When it's paired with the B band or the blue filter, we can actually compute a color index. And with color in astronomy, we can actually tell temperature. So this is actually really useful. And here we can really distinctly see that plateau and the drop off. And we can also see that it reaches its peak magnitude at about -14.7, which is really dim, even for a low luminosity event. And we can see that when we compare it against kind of a sample of larger supernova, which we're going to do here. So here we see ABFL, which is these black stars, plotted against some other low luminosity supernova, and then just kind of some regular type 2 supernova. And we can see the ABFL stands out as particularly faint. It's showing up here at the bottom of this plot. We can also take some other things away from this graph. As we can notice, some of these other supernova kind of have curves in the red and the yellow, and also in this pink one up here, while ABFL kind of stands out as being particularly flat. We can also notice that its plateau extends particularly long. ABFL only starts to drop off around 125 days, while some of them are dropping around 100, or like 110, which is kind of unique. And so we're going to quantify this. This plot is showing ABFL as a teal star. So on the x-axis, once again, we're having our brightness going from brightest to dimmest. ABFL is once again showing up on the very dim side. On our first y-axis, we're having, this is kind of a measure of slope. So if it was very steep, it would appear near the top, near this 3, and if it was very like flat, it's going to appear near 0 at the bottom, and ABFL kind of as a measure of 0.3. So once again, it's appearing near the bottom of this sample. And then this measurement is kind of how long the plateau is. ABFL's plateau is about 125 days, and it's appearing at the longer end of this measurement. So we can tell from this that ABL is faint, flat, and slow evolving. And this triple combination is a signature of the low luminosity subclass, and it once again just reinforces our classifications. Moving forward, we can model the volumetric light curve of 2024 ABFL, which will represent its energy output across ultraviolet and optical wavelengths combined. So once again, we're seeing ABFL appears near the bottom of the sample again, which once again, it is low luminosity, but it is dim even for being a low luminosity event. And another important thing we can get from this is the nickel mass, the tail end. To kind of talk about the importance of nickel mass, I'm going to talk about what powers these light curves. So in the early stages, the luminosity is sustained mainly by hydrogen recombination. And so as the hydrogen cools and then recombines, it releases energy that's keeping the brightness relatively steady, as we can see here. But after the plateau ends, the supernova's light is going to be powered by the radioactive decay of nickel into cobalt and then iron. And so the amount of nickel that's produced when the supernova explodes is really crucial, because it's going to directly affect how bright the supernova is once it falls off this plateau. And so for ABFL, we're estimating a nickel mass of about 1/100th the mass of the sun, which is a pretty small amount, but it does fall well within the range of some other low luminosity supernova, which we can see down at the bottom. And so up in pink, we have 2017 EAW, which is just a regular type 2 supernova. And as we can see, it would have a lot more nickel mass because its tail is just so much higher. Now we're kind of going to switch gears away from photometry into the realm of spectroscopy, which is the study of how light interacts with matter. And so this technique actually allows astronomers to break down light from an object and determine what elements are present based on the specific wavelengths that they emit or absorb. And so if we look at this periodic table, you can notice that many of the heavier elements, things like sodium, chlorine, and calcium, are actually forged in the depths of massive stars. So when we're studying things like supernova, we're not just learning about the explosions, we're actually learning about where the elements that are around us come from, which I think is really cool. I really think this is such a cool periodic table, because it just shows how interactive space is with things that we're interacting with every day in our lives. So astronomers, play this video. Astronomers typically look at spectra in the form of graphs, with wavelength along the x-axis and then our light intensity along the y-axis. And so this kind of smooth, doesn't look very smooth, but this curve here is called the continuum, and it represents the light that's emitted across all of these wavelengths. And then superimposed on this curve, you can see these emission features, or these peaks. And this is where specific atoms are emitting light. And each element has kind of a unique fingerprint. And so we can identify which elements are present by looking at where those features appear. And we can do this with 2024 ABFL. We've actually got a fairly comprehensive spectroscopic journey of it, as you're going to see in a second. Yeah, so here we have a series of spectra. If you want to focus on this hydrogen feature right here, you can watch as it changes over time, starting fairly small and then growing, and especially the absorption feature. It's going to get very large, and the emission is actually going to start to shrink in a little bit. This is a sign that it's expanding at first, and it's emitting and absorbing light, and then it'll start to move outwards in the ejecta. You also may notice all the different colors that are going on. Each color represents a different telescope, and each of these telescopes have their own resolutions, sensitivities, and observing conditions. And so even with all these differences, we can see kind of an overall evolution. Kind of going back to the beginning, if you want to focus on something else in this evolution, we can actually start to see some iron lines over here. We see some, let's see if the calcium will pop up, calcium right here. And then we can see some other metals like barium and scandium over here. We actually see our nickel that we used to estimate our dust at the very beginning. So it's very hydrogen heavy in the beginning, and then some of the hydrogen features start to fade away, and the stronger metal lines will appear. And now that we've kind of looked at more of a broader spectroscopic overview, we're going to kind of narrow down into like the very early times of supernova and explore some spectra there. So here is a NASA simulation that's going to show the earliest moments. It'll play. Is it going to play? It may not play. Dang, my other videos worked. Anyways, this video in theory would show a shock wave kind of breaking out and a burst of intense light. And this kind of intense shock wave breakout would ionize any of the material that had been shed by the star in its final years. And so that would be things like gas and dust that had been let off. And so if we were lucky enough to kind of catch the supernova in its first few days, you would actually be able to see this interaction in the form of these ionized emission lines. And these features can give us rare glimpses into the circumstellar material around the star and actually even the progenitor star. So what the supernova was like before it exploded. And we are lucky enough to have some really early observations at 2.5 and 3.5 days marked by these black lines. And so in these spectra, we can detect kind of this broad blue shifted bump right here, centered around 4,600 angstroms. And this has been detected in some other low luminosity type 2P supernova as well. That's what the other colors represent. And it's been thought to arise from a blend of some high energy lines that we can kind of see at the top, some oxygen, nitrogen, iron, helium, that have all originated from interaction with the circumstellar medium. This is still an ongoing investigation in my research, but studying these flash features gives us clues about the structure and composition of the material that's surrounding the star and ultimately the nature of the progenitor star. So it's definitely really cool to kind of look back at how the star was right in its early days. In addition to identifying elements, the spectra also allow us to measure the velocity of the material in the supernova's ejecta. And to do this, we can track how the spectral lines shift over time. So in this plot, we're identifying a couple of different elements. We've got our hydrogen alpha, our hydrogen beta, our iron, and our scandium. And so you'll notice that in all of these cases, ABFL, which is once again marked by the black stars, is kind of appearing at the bottom of the pack. In all these cases, yeah. And so this means that its ejecta are moving significantly slower than the more luminous events. And so this slower velocity is once again kind of a hallmark feature of these lower luminosity supernova, and it's consistent with a lot of the other traits we've observed so far. The dimness, the slow light curve evolution, and this low nickel mass. And they all paint a very consistent picture of ABFL as being faint and slow. So what's next for the future? I mentioned at the beginning that we did have some near infrared spectra. Here are two of them right now as I started to analyze them, and some of the elements we have. We are hoping to get some more near infrared spectra at later times, and this would actually help us to understand the cooling processes and dust or molecule formation, if that's actually occurring within the star. Another thing that we would hope to look at is the H alpha. I kind of mentioned earlier on that absorption feature, which is what we would call a P Cygni feature. It's very deep, and that's kind of unique. So we're kind of wondering why that feature is so significant and why it's not really in line with kind of the emission feature that's going on. So looking at that and comparing it to some other similar low luminosity supernova to see what conclusions they've come to. Another thing we're looking for is some late time spectra. As we can see here, there is no supernova. It is not visible. Currently, ABFL is hiding behind the sun, and it has been since March. So when you think back to our light curve, we actually only have one spectra that was taken on the radioactive tail. And so we would love to get some more of that because we would love to see how it's changed over these few months and if it does really look different on the radioactive tail than it does when it was on the plateau phase or even dropping off that plateau phase. So yeah, thank you guys.
We're gonna have our last talk of the day by Lauren.
Guys, I'm almost done. This works. All right, you guys. Hello, everybody. My name is Lauren Barkey. I'm a rising senior at Cal Poly Pomona. And this summer I worked with my wonderful mentor, Jeff Clayton, exploring the NEOWISE light curves of our Corona Borealis variable stars. A variable star is a star that changes in brightness over time. And our Cabors are known for deep decline events. So they decline in brightness up to 8 magnitudes due to dust obscuration. And I'll tell you all about that. But first, let me tell you about our Corona Borealis itself. So our Cabor was the first variable star ever discovered in the Corona Borealis constellation. And it is right here. And it is the first star of this kind ever discovered, so it gets the privilege of being the title of that category of variable star. And so Corona Borealis translates into Northern Crown. So here is a depiction of that constellation in an artist's depiction. Arcabor was first discovered and observed to be variable in the 1780s by a man named Edward Pigott in Bath, England. In Bath, he was taking observations over a span of years, looking at how Arcabor was changing. And what we care about here is the magnitudes. So he was watching how it was changing in brightness. Magnitude is a measure of brightness. And the higher magnitude is when the star is dimmer. The lower magnitude is when the star is brighter. And funnily enough, 230 years ago to this day, Edward Pigott was making an observation of Arcabor at one of its brightest magnitudes with something that would look like this, an opera glass. So it's not a very spectacular instrument. It's kind of like half of a binocular, but it got the job done. Now I want to tell you a little bit about the life story of an Arcabor. We've talked a lot about what happens toward the end of life of massive stars, but our Corona Borealis stars have a few different theories of how they were formed. The leading theory is that they were formed by the merging of two white dwarfs. And a white dwarf is a stellar remnant, and it's a stellar remnant of a star a lot like our sun. So we would start up on this path here. So you would start as an average star like our sun, burn through the hydrogen in your core, and expand into a red giant. The red giant would then eventually burn through all of its fuel to become a planetary nebula by expelling all of its material. And in the middle of that planetary nebula would be our little electron degenerate white dwarf. And what electron degeneracy is, kind of imagine a balloon. If you ever try to squeeze a balloon when it's full of air, it doesn't really want to go anywhere. It's kind of the same thing. Those electrons don't want to touch, and that pressure is what's holding up a white dwarf. And we think that Arcabors have formed through the merging of two different types of white dwarfs. So a helium white dwarf and a carbon oxygen white dwarf. And here's a depiction of what that would kind of look like. The stars would start interacting with each other and sharing their material, and eventually all of that material will become energized enough once it's all together to start fusion again. And after that, what happens, it will expand, it will puff up into our dusty, hydrogen deficient, carbon rich supergiants. And here is an image of some simulations of Arcabors, and my title has it, my talk has its title for a reason, because these stars are kind of playing peekaboo with us. Because what's happening is dust or materials being ejected out of these stars in little puffs of up to hundreds of kilometers per second. And once this material has gotten sufficiently far away from the star, it'll cool down into the graphite particles, kind of like Ben talked about. And then it will cover our star. And when it covers our star, we stop seeing light from it. And but what we are seeing is the glow of the dust in the infrared, like Aiden was telling you about. So this is the puff of dust coming in. This is in our line of sight. So if we were looking at that star head on, that puff of dust is coming through and obscuring our view. Now, my project used NEOWISE data. This is a light curve, first of all. This is the magnitude, so brightness, like I had talked about earlier, and time, so time of observation. And all the way on the far left end over here is the NEOWISE data. So a lot of work has been done on Arcabors, or a lot of observations of Arcabors have been happening for hundreds of years. This light curve is about 110 some years long. But we recently were able to obtain this data from NEOWISE. NEOWISE was the final mission of the WISE satellite after cryogenics stopped working and we only had 2 filters for observation. they usually use this scope for observing near Earth objects, so things like asteroids. But since it was observing this entire sky over a time of 10.5 years, 10.6 years, it was perfect for things like archivores, which are changing over time. And we recently have a catalog of 150 stars total of archivores ever discovered. And now we're able to look at them in these tiny segments of time. And now we're going to zoom into this left section as I tell you a little bit about my work this summer. So archivores exhibit a lot of different types of behaviors. And this is Euaquarii. It kind of does exactly what you expect it, what we want it to do actually. And this one's behaved really well. It's been my favorite to work with this summer. So this is, again, is a light curve. We have magnitude on the y-axis and time of observation on the x-axis. And this is the optical light. This is what we would be able to see visually, taken with scopes like Gaia and Atlas. And this is the infrared light. And what we see here is a brightening event, just right before a decline event. And that's telling us that the dust is forming just right before we stop being able to see light from the star. Now, another type of behavior we see is, this is just a star where we see multiple declines and corresponding incline events. So we have a brightening right here before this decline, a brightening right here before this decline. And then another type of behavior is with these. This would be one of the colder stars, but it's got a lot of activity happening, and we see some of the infrared changes as well, but not as much as we did in the others. Then here's a funny little guy. This is XX Cam. Me and Jeff talked about this one a lot this summer. This is a star that we've never observed a optical decline in, but here we're seeing an incline in the infrared, and that's telling us that if dust is forming, it's not forming directly in our line of sight, it's forming somewhere else in the star. And finally is a star, this is MV Sagittarii, and nothing's happening in the optical or in the infrared, but we still see this bright shell around that, which indicates that we still have that dusty shell. It's indicative of an archivore. And now some of the work that I did. This is the infrared light curve of Euaquarii with two filters, W1 and W2, but you might notice on the top we have a bunch of dots at one time. And I wanted to make this data easier to work with. So I took these dots and I grouped them into that time slot and took the median for everything in each time slot, so each NEOWISE epoch. And next, now that I had those easy to work with light curves, I started identifying incline events. So this is kind of tricky because with declines, there's been work done by one of Jeff's previous grad students with identifying declines in the optical light curves, where you have cutoffs for an onset, a minimum, and an end. But I hesitate identifying an end point for Euaquarii because we don't really see it returning to the same magnitude. But here is a maximum and here is an onset for that incline event. For this star, we have a maximum. We don't really know when it would have started. And we have an end. And right here is what I would call an onset, a maximum, and an end. Next, I worked on finding points in the optical data that corresponded with a point in the infrared data. So these here are all points within a certain time range of when a NEOWISE observation was made. And then I took the median of all these little group points to end up with this light curve. And if I had missing points here, I would have just done some interpolation by using the two, whichever points that were at the boundaries of those missing ones. And all of that was accumulating to this. This is so I could kind of get an understanding of when we find a best correlation between a incline event and a decline event and an incline event. So I take this entire decline and I shift it through the entire W1 light curve. And I'm trying to figure out when this R is the highest, and that will tell me if we have a correlation or not. And we see the highest correlation for this one at 180 days, so a step right after the original decline. And it's a negative correlation, which is telling us that we have a correlating maximum here with a minimum here. And then the next thing I've done is working with W1 minus W2. That's just, I'm subtracting these two filters, these light curves of two filters. And it's telling us about the color of the star, or of the dust around the star, which is an indicator of the temperature around these stars. The temperature of the dust around these stars. Now, what's next? This is, these graphs are different from what you've been seeing. These aren't light curves. This is on the x-axis, it's the hydrogen deficient carbon temperature class, which is an indicator of the temperature of the star. So the same grad student who's done that work on the declines did work to identify how, well, to categorize all these stars into a temperature class. So on the farther end, these are the colder stars. On this and the zero, these are the hottest stars. This one's not telling us much yet. Right now we have like a median of 180. This is the delta T. So do you remember that time shift graph I was showing earlier? This is that time shift. So that 180-day delta T that was on this graph here that's kind of what we're looking at here. And then here is the amount of inclines versus hydrogen deficient temperature class. And we're kind of excited about this because there is a little bit of an indicator that the stars that are hotter are seeing more activity in the infrared. But I do have 150 stars to work through, and that's what's next for me, is putting 150 more stars on this graph, so we can start making estimates and understanding the dust production mechanisms of archipores. And why that's important is because they are we're learning about these dust factories in a much smaller scale than things like supernovae. And I just showed you guys a lot of graphs, so I wanted to end my talk with some artwork. This is called The Kiss by Gustav Klimt. This was painted in the 1900s, early 1900s, and it depicts Dionysus and Ariadne. This is Ariadne here, and right on her crown, do you see those flowers? Would be Coronae Borealis, and we think that what's really neat is that Gustav Klimt might have had a little bit of an inside scoop, because Archipore is right here on that painting, so it makes its appearance there. And finally, this is something that I kind of saw earlier this summer on Instagram. And, this is a Skeety Pawnee tribe, so from Nebraska. This is a star map from them from 300 years ago. And Coronae Borealis is right here. I've had trouble, it is definitely an artist depiction because it's not very accurate, but I've had trouble exactly identifying if Archipore is here. I feel like it would be somewhere over here, but I kind of overlaid it. But I like to think that 300 years ago in the summer days in Nebraska, they're looking up and seeing Archipore at its brightest. And sometimes, and yeah, last but not least, I'd like to thank Jeff for making this such a fun project for me, and Patrick Tisseron for coming and spending a week with me to just go through the whole pipeline, Courtney and Jamie for helping me with the data and also just being there at 8 a.m. for us on early mornings on Monday, MMA for the support and the facilities for this to happen, and of course NSF for funding the whole experience.
So we're going to take any questions we have from the room first, and then I'm going to see what questions there are online. So anybody here? Christina?
Yeah, I've got one for like every presenter. I'll just start this. Is that okay if I do like 4 in one go?
right, I'm gonna take that as a yes. Okay, I'll go in order. Kaylee, talking about like the properties of the dust, like at one point you mentioned like the properties of the dust will also affect the attenuation. And I was wondering what kind of properties you meant by that, like size or like shape of the dust particles or.
That's a really good question. The composition of these dusts, like I said, there were graphite, carbon-based grains, silicate-based grains. Each one has different combinations of composition with elements. And so these all interact differently with light, and that's the dust property.
For Ben and Aiden, when you guys were describing the core collapse and then the shockwave, like during the supernova process, I was wondering like how long that actually takes. Like, is that like instant as soon as it hits that last point? It's like instantly we're collapsing and releasing that shockwave, or if it's like fast only in terms of space, where it's still like super long time.
Once it hits iron at the center of the core, it is a matter of days, I believe, before it begins the collapse process, because that iron is.
Yeah, it's real quick. As soon as that force disappears, the outside force will win.
And then for Maddie, when you were talking about, so like some of the materials you were talking about, like them, like not only it being dim, but also them being really slow. Does that slowness contribute to the low luminosity, or are those just like two characteristics that were happening to be like both with those low luminosity ones?
So one of the properties of like low luminosity supernova is that they are slow expanding. So it's kind of like the correlation, like it's slow because it's dim, and it's also dim because it's slow. So they're very tied in with each other. So that's definitely something I'm also still researching into, because especially with that, I was talking about that and that big key Sydney absorption. Is we're wondering if that is affecting the slowness, or if that is something else that's still in it. Because when we're measuring those expansion velocities, we're taking kind of like the lowest point, which is often that absorption feature, so that can actually affect its expansion velocity.
Then my last one for Lauren, with I like the image of like the dust, if it was like coming at us, and then like seeing like what it would look like against the light. If the dust was forming behind the star going away from us, would we have any way of knowing that's happened?
I know that if it's coming out on any other point, we would be able to see a
little
brightening event. I'm not sure about directly behind the star.
Well, as long as, if it's right behind the star, you're gonna see it, as long as it's around the
But
star.
like, yeah, like even if it's around, as long as it's
Yeah.
around.
Oh, I was just gonna be like days. When you said fast, I think I'm like seconds. Like, is that like too fast? Like, does anything in space happen?
Well, like think about the main sequence of our sun. We're 4.5 billion years into our sun's light, and it's gonna keep doing what it's doing for another 4.5 billion years. So this is like a different stage of stellar
Fast and
evolution that's
relative
happening in days. So compared to that, it's almost insignificant.
These are great talks, a lot of questions, possibly. So you mentioned absorption and scattering. Those are two different phenomena. Can you figure out a way of distinguishing one from the other? Is that even important?
It is important, it's
Yeah.
called albedo. So so if you imagine a dust grain that's completely black, it would absorb everything that hits it, and one that's white is going to reflect almost everything. And so you actually can tell how much is being absorbed and how much is being scattered.
And what do you do you see a predominance of one versus the other in these stars?
It would be different for different kinds of grains, because they would, like the carbon ones tend to be very black and absorb most of the light, whereas other elements would be would reflect more of the light.
That's one more thing. So there's a lot of energy coming out of these end of life stars. And you're looking in one part of the spectrum, I suppose, and it's surely with X-ray. Are there X-rays also being emitted in these death throes?
Short answer, yes.
Yeah. And they will interact, that will interact with the dust and probably ions and so forth, so there could even be ions, I suppose, and plasmas out there too, so it's a real mix of
Yes,
stuff.
it's, when a supernova goes off, it's a big mess.
Yes, this is a related question for Kaylee, but I think in your presentation, you said that dust interacts most with UV light. I'm curious why that is.
Yeah, so the dust grains are the same length as the wavelength. So the wavelength is the measurement of that wave. And the dust is the same width as that wavelength. So if we go into longer wavelengths, that dust grain is going to be a fraction of that length. And so it interacts with it more because they're the same size.
I have a question for Lauren. You mentioned that in the conclusion of your project, you were trying to prove that hotter stars had more activity. I was wondering like how you can use the temperature of the star versus the temperature of the dust to search for more incline events.
Sorry, can you ask that again?
Yeah, I'm just, you said that in the end, hotter stars had more activity.
Yeah.
And like, I was just wondering the relationship with temperature and searching for incline events.
Okay, so the relationship between temperature and searching for events is that we just want to see if we're trying to figure out if there is a relationship between the temperature and incline events, because we have seen that there is a relationship between the temperature and decline events. So work has been done that has shown that the cooler stars exhibit more decline activity. Yeah.
Yeah.
TBD.
Yeah.
Any more questions here? I just wanted to say that John Briggs, who's when watching the talks, and he was the first male intern in the astronomy program in 1977. Joanna, would you like to say anything before we sign off?
First of all, and I want to say that it really is our pleasure to have our new interns here and all of you here every summer, and that this work is so important. The reason I was late is I came from a talk that was being given by the president of Fordham University. And one of she talked about two things that struck me that's relative to this gathering tonight. One of which she said how important internships were to college students because it singularly defined their ability to pursue their careers. And I thought that was really interesting. And then the other thing that she referenced was how important STEM education was. And that it's critically important right now in our country, in the academic environment, that we invest in STEM education. And all of you here are part of that in some way, shape, or form. So I hope that this has been as valuable for you as it has been for us. Thank you.
Thanks, Joanna. Okay, everyone, thanks very much for coming, and goodbye.